welcome to the Line of Best Fit podcast. So data that model linear functions. Can the amount of a solvent that can be dissolved in water as a function of temperature be described with a linear function? If so, what's the equation that models the data? Sometimes data points will be scattered all over a graph and they don't seem to follow any pattern. There's no relationship between the two variables. We know that there's no correlation between the two variables. Sometimes there's a pattern between the points that is a linear pattern. There's a relationship between the variables that we can describe with a linear function. Mathematicians call this line the line of best fit or a regression line. So we're going to be looking at finding lines of best fit both with and without technology. So by hand and using technology. And you need to be able to use both methods. All right, so let's learn a little bit first of all about linear regression, which is the mathematical term for finding a line of best fit. And my page did not turn. All right, so scatter plot. So a graph used to determine whether there is a relationship between paired data is a scatter plot. This relationship is described as correlation. And so we already have one vocabulary word, and it was on the other page, but let me see if I have it again. I think I have it again a little later on. All right, so you can wait to fill in your notes. All right, so here the relationship between paired data is called correlation. So our objectives are to fit scatterplot data using linear models with and without technology, and use linear models to make predictions. And we'll also decide about the validity of those predictions. Some vocabulary for us. We're going to learn about regression, correlation, line of best fit, correlation coefficient, interpolation, and extrapolation. So researchers, such as anthropologists, are often interested in how two measurements are related. The statistical study of the relationship between variables is called regression. That is the first vocabulary word in your notes, so fill in this word in your notes. There we go. And here, those anthropologists are unearthing a dinosaur or something, some other type of creature, prehistoric creature, and maybe they're going to study something about that creature. Maybe is there a relationship between the animal's the length of his legs and his height, or is there something they can use to study the age of that fossilized animal there? So lots of different fields will use statistical study and regression analysis. All right, so there's your second vocabulary word. The correlation coefficient, R, is a measure of how well the data set is fit by a model. So this is your second vocabulary word that you need to add to your notes. And you have this in your notes as well. Properties of the correlation coefficient R. So first of all, R is a value in the range of -1 to 1. And so our correlation coefficient cannot be less than -1, and it can not be greater than 1. If you're a straight line with a positive slope, if the correlation coefficient is 0, the data set has no correlation. If your correlation coefficient is -1, the data set forms a straight line with a negative slope. The closer the correlation is to 1 or -1, the stronger the relationship is. All right, it's not giving us the slope. So correlation coefficient is not slope. Right? It measures the strength of the relationship, not the slope of the line. And that is not in your notes. I would like you to write that down, because sometimes students get slope and correlation coefficient confused and think it gives us the slope of the line. It does not. right? It tells us something different. And it's measured by measuring how far away each of the points is from the line of best fit, from the regression line. So I'd like you to write this in your notes. Right, there's plenty of room underneath this diagram that's in your notes. So the correlation coefficient measures the strength of the relationship, not the slope of the line. And the closer it is to 1 or -1, the stronger the relationship is. Okay. So here we have let's label these, because you have these in your notes. Let's label them by their strength. So this is the first figure here with the correlation coefficient of -0.95 here is a strong negative correlation. And those points are very much on that line there. The one next to it, -0.6, that's not weak. That's not weak. You may look at it and say, oh, those points aren't close enough. But they're actually, they have a definite linear trend there. This would be a moderate negative correlation. If we get any less than that, perhaps -4, then we start to call that would be a weak. So this is a moderate negative correlation. A little bit more space to write. This here is where it's almost 0. And it says approximately 0. You never really get exactly 0 generally. You might get almost 0, like 0.01. That's no correlation. Right, those points are not following any type of line. Right, that's no correlation. All right, next to that, we have a moderate positive correlation. So whether it's when we have a negative correlation, the points are following a line with a negative slope. We have a positive correlation, the points are following a line with a positive slope. So we have a moderate positive correlation. And we'll talk more about correlation in terms in context. And then one more. Here we have a strong positive correlation. All right, so label those in your notes. Okay. Label those and then add this piece of information right here. Keep writing, there we go. I keep writing notes and it wasn't popping up. There we go. So add that sentence to your notes so that it'll be clear for you. Okay, so I talked a little bit about correlation. All right, let's take a look at some more examples. So you have some in your notes. These ones aren't in your notes, but here we have some more examples. So positive correlation, the relationship between paired data when y tends to increase as x increases. It's shown by a scatter plot where the plotted points generally rise left to right. And so notice the points are following a positive trend. They increase as we look at them left to right. And 0.89 is a fairly strong positive correlation. Not as strong as 0.95 in the other diagram, but pretty strong. Negative correlation. So the relationship between paired data when y tends to decrease as x decreases. So here we have a negative correlation. It's shown by a scatter plot when the plotted points fall from left to right. Right? So they're following a negative trend, they're decreasing. Right? So actually here on both of these we had a one in context. Here, so with the positive correlation, your grade tends to increase as the hours studied increases. Those are positively correlated. The more you study, the higher your grades tend to be. Here we have a negative correlation because the more hours you spend watching TV, the more your grade tends to decrease. Right? So and so we have negative correlation, and then we can also talk about the strength of the correlation. So the more closely the points are to forming a line, the stronger the correlation is. Right? So there in the top example, we have a strong negative correlation because those points are very close to being on that line. A little bit weaker correlation, our points are further away. And correlation coefficient is measured by finding the distance between the points and the line. That distance is called residuals, but that's just some extra information for you. So relatively no correlation. The relationship between paired data when a scatter plot of the data shows no linear pattern. So here we have no correlation. Looks like a cloud of points. This is some questions I'm going to ask you in class, so you can't see them. So a scatter plot is helpful in understanding the form, direction, and strength of the relationship between two variables. And actually we have a vocabulary word for you, and actually we filled this one in already. Correlation is the strength and direction of a linear relationship between two variables. So we had already filled that one in. But I'll just underline it again. And this is in your notes too. If there is a strong linear relationship between two variables, a line of best fit or a line that best fits the data can be used to make predictions. We're going to be working with, so we can have different types of regression. We're going to be working with linear regression. We're going to be working with data that's best described by a line. We could have other types of regression as well. We could have quadratic regression where it follows the data points follow a parabola, or we could have exponential regression where it follows an exponential curve, or it tends to increase, where the rate of increase is increasing as x increases. But we're going to be working with linear. Linear, we can write the equation by hand. The other types of regression are a little tougher to write the equations for, and we generally need to use cytology. All right, and in your notes, I want you to underline the word best fits and put the word describes. So when we say a line that best fits the data, we're talking about a line that best describes the data. And then underline used to make predictions, because that's what we're going to be doing with our lines that best fit those equations. We're going to be making predictions. And a helpful hint. You want to have the same number of points above and below the line for your line of best fit. And actually, there's some space on your notes. Add my helpful hint. If you need some time, just pause the tape and add that helpful hint. All right? Have as many points above and below the line of best fit. We want the line to just go bursting through those points and be right in the middle. And let's look at the steps. We'll come back and define those two words in your notes, but let's look at the steps here. So approximating a line of best fit by graphing. And these are the steps for graphing. These are going to be by hand. Right, so we're going to draw a scatter plot of the data. That's the very first thing we do. Right? When you're drawing your scatter plot, do not truncate the graph. In other words, don't have different scales. Don't jump from 0 to 40 and then go up by tens. Right? That distorts the graph. We're going to make sure that the x and y values go up by every single space is worth the exact same number. Right? It will distort your graph if you don't do that. We're going to sketch the line that appears to follow most closely the pattern given by the points. There should be as many points above the line as below it. Choose 2 points on the line and estimate the coordinates of each point. You want to do as little estimating on that as possible, so you want to choose the clearest points you can. Right? The ones that, if there are 2 points that are, that are right, and we're always going to graph, by the way, on graph paper. A linear regression not done in graph paper is absolutely useless. It's just, you may as well just make a guess on what the equation is. But as close to points that are integer values as possible, or maybe halfway points between integer values, because we want to do as little estimating. We want this to be as accurate as possible. We're going to find the equation of a line that passes through the 2 points, step 3. To do that, we'll find the slope between the 2 points. We'll use a slope formula. And then we'll use point-slope form and a point to write the equation. This is the equation that models the data. I have the very important in your notes already. The very important is the 2 points must be on the line when you write the equation of the data. They don't have to be data points. Do not choose 2 points near the line just because they're data points if they're not on the line. Right? It does not matter whether or not whether they were actually data points, but the points have to be on the line. Right? And so the 2 vocabulary words above before we look at a scatter plot. I think we'll do one together on this podcast before it ends. We have interpolation and extrapolation. So interpolation, predicting using the line of best fit for values between the data points. So inter means between, right? So they weren't exactly data points. Like, so maybe we had data on like 5, 15, and 30. And we wanted to know about what y would be if x were 10. Right? So that's not a data point, but it's in between other data points. That's more accurate than extrapolation. Right? Extrapolation is predicting using the line of best fit for values beyond the data points. Because the reason it's less accurate is that the pattern may not continue. Right? So for instance, if you think about growth of a child, right? So you grow a lot as a baby, you grow a lot as a kid through puberty, but then after puberty, you don't grow so much. So if we were to use an equation that used your height and ages when you were between the ages of 0 and 12, and then try to predict your height when you're 70, we would get a pretty silly answer. We'd probably get an answer that you're like about going to be 12 feet tall. And that would be ridiculous because you're not going to keep growing. Right? And that's the problem with extrapolation, is that the pattern may not continue forever. Right? So we have to be careful when we use extrapolation. Interpolation, though, is much more accurate, right? Because we're looking in between values we already have. So we know the pattern exists between the values. So values determined through interpolation are generally more reliable than values determined through extrapolation. The further the data is extrapolated beyond points in the graph, the less reliable the prediction is. The pattern just may not continue indefinitely. Okay? So make sure you have these in your notes and you know those vocabulary words when I use them. And understand what they mean. All right, so we're going to do one problem together, and this one is not in your notes, so just sit back, relax, and listen to me explain how to do this one. All right, so Albany and Sydney are about the same distance from the equator. Make a scatter plot with Albany's temperature as the independent variable. Whatever your independent variable is, that is x. X is always independent, y is always the dependent. We're looking at the relationship of the dependent variable to the independent variable. Name the type of correlation, then sketch a line of best fit and find its equation. All right, so we're looking to see if there's a relationship between the temperature in Sydney given the temperature in Albany. So since Albany is going to be our independent variable, Sydney is the dependent variable. So the points that we're going to be graphing are Albany as the x, and Sydney's temperature is the y. So 3065 and 3466 and 41, I may as well write the rest of these down here instead of the ... 41, 63, 50, 58, 59, 53, 67, 49, 70, 46, 70, 48, 62, 52, 51, 56, 40, 60, and 3363. Oops. Okay? Right, so make sure you know which variables are independent, which ones are dependent. Right? Otherwise, you will definitely not have your scatter plot set up correctly. All right, so our next step is to graph, and I actually have this graphed on the next page. Ta-da! All right, so we plotted the data points, and we want to identify the correlation. So if we look at those points, notice that as Albany's temperature is increasing, Sydney's temperature is decreasing. Right? So the temperature in Sydney decreases as the temperature in Albany increases. Therefore, our data set is negatively correlated. Right? So as the temperature rises in Albany, it falls in Sydney. Right? So we have a negative correlation here. All right, so we want to sketch the line of best fit. That's been sketched for us. All right, when you draw it, notice you want the points to be on either side as close as you can. And notice how it kind of follows the pattern of the points. Right? It's going the same direction. Sometimes it takes a couple tries before you get that line just perfect. And actually a little trick is using a piece of spaghetti. Because it's so thin, you can easily see the pencil, and you can use that to figure out where your line should go. So it works really well. A piece of spaghetti when you're graphing lines of best fit. All right, so we've got our line that splits the data evenly above and below. We have to now find the equation of our line. All right, so we want to identify 2 points on the line. You want the best 2 points possible. All right, so I'm looking, I don't have any integer values here. I'm looking for maybe a halfway. Well, actually, these ones, a little tricky. This one's, each one of these boxes is 10. So if I can find one that looks to be maybe a fourth of the way or half the way on that line, that would be pretty good as well. Let's see. I guess I'm going to take this point right here. That one's not too bad, all right, because it's halfway. It appears to be halfway right there. All right, so each one of these lines is 10, therefore that's 5. So that's 85 on the x, and on the y it's pretty good, it's 40. So 85, 40, that's 1 point. And then I need to find another. I'm going to try to stay away from that 80. It's a little off, and I don't want to make the assumption that 80 is my y-intercept unless I'm 100% sure. And so, boy, trying to find another good point. Let's try maybe this one here. If I go across, so notice I'm just choosing points on the line. They're not necessarily data points, right? There's no data point near that line I drew. And while there's a data point close to this line, that point is not on the line. I just want to, whoops, no, I want to move you up. I don't want to do anything but move you up. I guess it does not want to be moved up. Yeah, that feature does not like to work when I'm trying to do this. So let's try this again. There we go. My line's got a little glitch there, a little bubble there, but it's okay. The end started off straight. So that looks almost to be maybe, maybe about, I'd say there's about 6 below, maybe 4 above on that point. So maybe on the y, the x is easy to figure out. That's 50. The y right here, well, imagine that's on the line. Not exactly where it ended up after I drew it with the smartboard. Appears to be, I would say, 50, 60, excuse me, this here would be 50, so maybe 50, 56. Right? It's a little bit more than halfway. Right? So sometimes it's easier, sometimes it's a little trickier. Maybe this would have been a better point right here. Still not at the halfway point. Maybe it's pretty close. So you can't answer me to say, which point do you think is better? Let's maybe take that one. I think it's a toss-up, but let's take this one. All right, so this one is 10, and that would be 75. Let's take those two. All right, so those are, we got the best points we could find. All right, and so we're going to take the slope. All right, so we take the difference in the y's. right, so let's just write that down so you remember. Difference in y coordinates over difference in x coordinates is going to be 75 minus 40 divided by 10 minus 85, which is going to be 35 and 75. I'm going to keep it as a fraction because that's not going to be a terminating decimal, but I'm going to reduce. So they're both divisible by 5. So this would be 7 and 25. 7 and 15. 7/15. All right, so that appears to be our slope. All right, we want to find, we got the, we did the slope of the lines right there. The 2 points that we used are 10, I wrote them on the graph, 1075 and 8540. All right, and now we'll write the equation in point slope form. And that's the last thing we're going to do on this podcast. All right, so I'm going to pick either one. I'll take 10 and 75 because I like the numbers better. All right, so I have, remember, point slope is y minus y1 equals m times x minus x1. Get to review linear functions. All right, so, and I'm going to use that point. So y minus 75 equals, and oops, I put 75, bad me. 10 minus 85 is negative. Negative 7/15 times x minus 10. We'll distribute that, right, and that would reduce. So we have y minus 75 equals negative 7/15 x, and then it's going to be a positive, a negative times a negative. And then, well, that would be 70/15, right? 7 times 10 over 15 times 1, 70/15. So negative, well, I'll leave off the negative because, you know, the two negatives are going to be positive. So I'll just leave out the two negatives. But 7/15 times 10 is going to be 70/15, and that would reduce. Or you could recognize that those two numbers you can cross-reduce on when you multiply. They're both divisible by 5, so this would be 3 and 2, which means this is going to be 14/3. Or you can divide 70 and 15 by 5 and still get 14/3. All right, so we have y minus 75 is equal to negative 7/15 x plus 14/3. If I want to add 75 to 14/3, I have to change that to thirds. All right, so we're going to, if the denominator is 3, I need to multiply the numerator by 3, right? Because it would be, as a fraction, 75 is 75 over 1, right? And so 1 times 3 is 3, and 75 times 3 is 225. I know I did that really quickly on top of my head. I'm not confident in my answer for sure, unless I'm right, and which I am. So I'm totally confident. Why I doubted myself, I have no idea. Oops, except then I wrote 5. We're almost done. We're almost done. Sorry if this podcast is a little long, but you mostly just had to listen to me. All right, so now we have y equals negative 17/15 x, and then we add those two together, and that's going to be 239 plus 239 thirds. So I was glad I didn't say 80 as a point, because really it's not at 80, and I really couldn't estimate how much it was over. It was just a teensy bit. Teensy bit sometimes is hard to estimate. It's easy, halfway point's easier to estimate. And there we go. That's our linear regression line. So not too bad, right? You graph them, you draw your line of best fit through the data points, you pick 2 points that are the best 2 points you can find. Sometimes you can find good points, sometimes you have to really look really hard. And so, by the way, those 2 points are not data points. There are 2 points on the line, right? 2 points on the line. And it doesn't matter if they're data points. And then you use those 2 points to find the slope of the line, and then you use point slope to write the equation of the line. And then you just simplify. And there it is. So thanks for watching the podcast, and I'll see you in class. Bye for now.